So today we'll just brush up what we covered in the last class and continuing the same session with the different criteria. So in the last class we briefly discussed about statement of sampling theorem. So two important factors in sampling theorem are it is concerned with band limited finite energy signal and how this analog signal can be converted to digital with the help of the some sampling process conditions. So the conditions like it's a sampling frequency or the rate at which you are going to cut your band limited signal should be greater than or equal to the twice of the maximum frequency component of that analog signal. That is very important condition that is going to make your sampling theorem. Then we go on with discussing the sampling process with the help of the instantaneous sampling type of process, where we have considered an analog signal having this kind of shape g of t. This has got multiplied with the train of impulses located at the interval of ts. You can see s dou of t. So we are multiplying our analog signal with the help of this train of impulses s dou of t, where impulses are spaced at equal intervals of time, that is ts seconds. So that is going to give us a g of nts. So g of nts is nothing but a sampled version of your analog signal g of t. So where it is going to looks like you can see here sampled signal observing here g dou of t. So you are multiplying two time domain signals here, g of t with the s dou of t. So we are not, it is not possible to multiply two signals in time domain. We'll apply the convolution theorem here, as you can see here. So we'll apply the convolution theorem. Then we are able to get this g dou of t. So that can be done in two successive stages or two steps. So first you can see what the sampled version of the signal we are getting here. G dou of t, that is nothing but the product of g of t and s dou of t. S dou of t we have assumed it as a train of periodic impulses. That is nothing but the summation all the way expanding from minus to plus infinity. That is from left to right side of your x-axis. So dou of t minus nts. So this one is the s dou of t. So this one is g of t, which we are going to multiply in the time domain. So first initially we started the mathematical discussion by assuming what g dou of t we are getting and what is s dou of t. G of t we cannot assume because we just said that said it as just an analog signal. Next, substituting, making use of equation 2 in 1. So what we can get finally like this here, and applying the shifting property of impulse function, we are arriving at the equation number 3. So this is the first step, guys. So after this one, what we have did, we gone for converting, gone for discussing our mathematical version in terms of frequency domain. So you can see here, we are multiplying two signals in the time domain. We have taken the help of frequency domain conversion with the application of the Fourier transform on both sides. So now we can easily multiply their equivalent frequency spectra in the frequency domain. So by this one, what we are getting is equation number 5. So 4 and 5 are these two equations. We are getting the step number 2, that is a frequency domain conversion. So later by applying the convolution property of impulse function, we are reaching at equation number 6 and 7. So you can see in equation number 7, it will contain the main impulse located at the origin along with plus Fs summation n not equal to 0 g of f minus n of s harmonics. Means these harmonics will be eliminated by passing this equation number 7, that is signal, through the low pass filter. Means idea here is that of course we are discussing in terms of frequency domain, but actual thing what is happening is there when you are going to multiply analog signal g of t with the train of periodic impulses s dou of t, and when you are going to pass that product signal through the low pass filter, so these harmonics are the frequency components containing the high frequency values will be avoided by passing it through the low pass filter. It is allowing the low frequency components only. And later we are simply applying the inverse Fourier transform to get back our g of t. Now that's how you can see the recovered g of t signal from the sequence of these sample g of s, g of f is going to be similar to the sync kind of a signal. So these small peaks you are getting symmetrically located on the other side of the origin, which is happening because low pass filter is not going to eliminate almost all the harmonics here. Still some harmonics will be left out. So those are appearing along with our recovered original signal G of t. So this is the simple way of sampling process we have discussed as under the name of instantaneous sampling here. Now continuing the discussion here with respect to how we are going to achieve this band limited sampling process. Now the sampling theorem is normally stated strictly, you can see here, strictly for band limited signals having finite energy. So these two terms are very important here. Your signal, what you want to transmit, it should be band limited. Suppose if you are using the sampling theorem. And normally, everywhere we are adopting this sampling theorem. So with respect to 2 points, we can elaborate this one, how this one is strictly applicable with respect to the band limited signals. Band limited signal having finite energy means it has the frequency components less than or equal to W hertz. Hertz means number of cycles per second. Means how many cycles we are transmitting in 1 second. That's the meaning of hertz. Like that, we are transmitting W hertz, W cycles per second. Means if you have any kind of a band limited signal having finite energy with the frequency of less than or equal to W cycles per second, then such kind of signal is completely characterized or described by its instantaneous values separated by 1 by 2 W seconds time. So are you getting this one? So the first inference what we are getting here is that such kind of band limited signal having the frequency of W hertz can be completely described in time domain by its instantaneous values separated by 1 by 2 W seconds. Means it's a reciprocal of twice the frequency of the band limited signal. So that much of time spacing in terms of seconds will be there between successive samples of this band limited signal after doing the sampling or cutting that band limited signal. So that is the sampled version we are getting here. But how to get back our recovered signal, that is a G of t. So that another statement is also there. Such band limited signal can be successfully recovered from these samples what we got after cutting the continuous time signal at the rate if you are taking 2 W samples per second. Now for every 1 second, 2 W samples then we are able to reconstruct back our original signal without any difficulty. So these are the two important criteria or conditions which will guide us in sampling our analog signal to get it converted to sampled version. And second one, we have to take 2 W samples per second to get back our original signal G of t. So this rate at which we are talking that we have to take the 2 W samples for every 1 second, as far as concerned to the band limited signal having W hertz is called Nyquist rate, and 1 by 2 W is called its Nyquist interval. So here you can see, guys, one simple diagram has been shown here. That is a frequency domain version. The first one figure it will indicate G of f, that is a band limited signal. G of t the frequency domain versions, the frequency spectrum of the band limited signal. You can see its band is limited from minus W to plus W, means its bandwidth is 2W, having energy of G of 0. So when you can take its sampled version, you can see each of these bands are located having the bandwidth of 2W, are located without any overlapping, and they spaced at 1 by 2W time period. So when you take such samples at 2W samples per second, then we are easily getting back our G of t back. We have to apply I of t there, then we will be able to get mathematically, in theory we are talking like that. But practically, we have to take 2W samples for every 1 second by some circuitry means. Then we are able to get our original signal back. So this is the sampling process what we are talking here with respect to these two conditions, how faithfully we are able to do the sampling and get back our original signal from the samples without any over sampling or under sampling. So that's what the first further thing we are going to discuss. So the concept of over and under sampling. So the correct sampling we are getting when the sampling frequency is equal to the 2W. So we can see here, we are not getting an overlapping between successive samples here. Remember guys, we are discussing these samples in the frequency domain because we can easily visualize these samples here. But when you can decrease the sampling frequency less than the twice the frequency component 2W, then you can see we'll start getting the overlapping is happening between the successive samples. That is known as an aliasing. Aliasing effect will start occurring when we'll start getting the sampling frequency decreasing less than the 2W. And reverse of that will happen if you increase the sampling frequency more than 2W. In that case, you can see we are getting the samples are widening, becoming apart, having some guard band here between them, separation between them. So that is going to appear as something like a discontinuous waveform. That is a loss of information, we can say. So overlapping will happen. There also we are losing some information. So gap is also occurring. In that case also we are losing some information. So in either case, either under or over sampling, we are going to lose some information. So that can be avoided with the help of by keeping the correct sampling condition, that is Fs equal to 2W. So based on this, some simple problems might be asked, quite frequently asked in the examination also. So these things I hope already we have studied in analog or digital communication subjects. The same thing now we are going to repeat. So this one is an analog signal he has given you in terms of an sine and cosine terms here. 3 cos 50 pi t, 10 sine 300 pi t plus cos 100 pi t. So 3 sinusoidal terms are there, that is going to make up your analog signal. Now what he is asking you to calculate the Nyquist rate and Nyquist interval. So what you have to do, we have to first find out what are the frequency components involved in each of these sinusoidal terms. So all of you listen here carefully. So what we can do, we can simply compare the given equation with the standard equation. There is a 3 cos 50 pi t, you can compare with the 3 cos omega 1 t. tan sine 300 pi t you can compare with the tan sine omega 2t, like that omega 3t here. By comparing equation 1 with 2, we are able to get omega 1, that is f1, omega 2, that is f2, omega 3, that is f3. Then we have to find out the maximum of these three frequency components. So why you have to take maximum? Because W it will indicate the maximum frequency component. So that's why we have to take into account of the maximum frequency component as far as the sampling theorem or process is concerned. So the maximum frequency out of these three frequencies is going to be 150 Hertz. So from this we can easily calculate the Nyquist rate, that is going to be equal to twice the uh, FM, that is 300 Hertz we are getting. And Nyquist interval we can easily get, that is a reciprocal of this one, that is we are going to get it as 1 by 300, that is a 3.3 milliseconds. So very simple problem. The similar problem I have quoted here, another one, second one for you to practice here. So I hope you can do this one at home. So this is a very simple concept we discussed today, over and undersampling concept, that is an extension of the sampling theorem, along with some very simple numericals based on the sampling process. So next we can continue our discussion today with respect to the pulse amplitude modulation. So pulse amplitude modulation is a very important modulation technique widely used in the communication systems. So here what we are doing in simple terms to explain, here we have the message signal G of t, that is an analog signal. And the second figure we can see it is showing you the a train of pulses, that is indicated by S dou of t. And if you multiply these two, the product of these two has been shown by G dou of t, that is a sampled version of the signal G of t, that is called G dou of t. So what we are doing here is that a train of rectangular carrier pulses, train of rectangular carrier pulses are varied as per the sample values of the modulating signal. So here you can see how we are getting PM signal, pulse amplitude modulation. Actually, it is amplitude modulation, but it is pulse. Means why we are using pulse here? Because we are using the sample values of the modulating signal. So like that you can see here the G dou of t you are observing. The sample values of these sample values of the modulating signal we are using to change the pulses of the rectangular pulses of the carrier signal. So finally you can see the envelope of what we are getting, it is going to follow as that of the G dou of t. So simply we have to vary this train of pulses P of t. We are going to use sampled signal. How you can see here, the sample, each sample its amplitude is going to vary here. So these instantaneous variation of the samples in 0 of t is going to vary the rectangular carrier pulses. Then finally we are going to arrive at this PM version. Finally what it has been shown. So I haven't came across any kind of a mathematical discussion as far as the syllabus is concerned here. So later we'll see here if it has been asked in the exam or if it is required. We'll go. Simply we have to explain the equation and these figures, whatever the steps I just explained in that way. So the advantages you can see it is the main and very important base for all digital modulation techniques. Disadvantages, due to Nyquist criteria, it requires high bandwidth for transmission because of the Nyquist criteria. Because the pulses we are involving here, the pulse width is also going to consume some of the bandwidth here. That is going to matter here. So because of this, the amplitude keeps varying, so there is a noise associated with it. Because the amplitude is going to vary here randomly, we cannot predict it. Because of that random variation of the amplitude of the pulses, some noise will be encountered and high bandwidth. So these are the two key issues with the PAM. Besides that, it is the main important basis modulation technique for the digital motion is concerned. So far we discussed the concept of sampling theorem. It's a mathematical discussion we did there. Continued that one in terms of the over and under sampling concepts, some numericals, and pulse amplitude modulation we have discussed here briefly today. So if required in detail, if it is required, we'll go with the pulse amplitude modulation in the next session. And this is also known as a flat top sampling because the samples will be kept, the top you can see it will be kept flat. So that's why it has got its name as a flat top sampling. So that's all.